Question 1 wants first of all the structural formula for this compound 2-chloro-3-methylbutane. I think that structural formulae are pretty horrible. It's easy to make mistakes with them. I would be inclined firstly to write down the skeletal formula just because it's much more, visually clear what compound you've got. So 2-chloro-3-methylbutane. Butane is a chain of 4 like that, and 2-chloro means you have a Cl on carbon 2, that's the second one along, and a methyl group, which is just a 1 carbon branch on carbon 3. So that is the skeletal formula, but that of course doesn't answer the question because it wants the structural formula. But now you've got that in front of you, you can just go through and get the structural formula in place. So the key to that is that you've got to get the right number of hydrogens on each carbon, and you do that by recognising that carbon must always form 4 bonds in a stable compound. The only time it doesn't do that is in intermediates like carbocations or radicals. So here you can say, right, this carbon has only 1 bond shown, so there must be 3 more, and those must be to hydrogen. So that end carbon is CH3. Now this one, you can see the carbon has 3 bonds in place, so it has only 1 left for a hydrogen, so that's CH, but also Cl there. So that's that carbon CHCl. And this carbon has 2 methyl groups attached. So you can either write it, so first of all it must have 1 hydrogen again, because you can see otherwise it would have only 3 bonds. So you can either write it like this, CH3 twice, or you could write it like this, where you just treat one of the methyl groups as a branch and then the other one as an extension of the chain. Either of those would be fine. Right, so the second question is wanting us to compare the volatility of that compound with 3-methylbutan-2-ol. So ol means an OH group, so 3-methylbutan-2-ol is that. And volatility, remember, is about how easy it is to turn it into a vapour. So we're talking here about the strength of the intermolecular forces. So what you explain is that this can form hydrogen bonds, because remember, anything with an OH group can form hydrogen bonds, whereas this compound that we're comparing it with can't, because it obviously has no OHs or NHs or FHs. So this can only form other kinds of intermolecular forces, but you should always specify if you can. So it can form induced dipole-dipole forces, because everything can do that, but it can also form permanent ones, because it's got a polar bond there. So we could say induced and permanent dipole-dipole forces. So that's at the heart of the comparison, and the key point, of course, is that hydrogen bonds are stronger. So you need to say that hydrogen bonds are stronger than other intermolecular forces. Okay, so that needs saying explicitly. And then you need to relate that to the volatility, and that means you have to talk about the energy. So if those are stronger, so it takes more energy to break them. And if it takes more energy to break them, that means it's not going to happen so easily. So you're either going to have to go to a higher temperature, or you're just going to have to wait longer. So it takes more energy to break them, and therefore the alcohol, which is this, is less volatile. Okay, so we've done lots of those physical properties questions now, so hopefully you're getting up to speed with the approach to doing those, and then once you've done that, those questions are a bit of a gift. So the next task is to synthesize this haloalkane starting from an alkane, it says. So that means that the carbon skeleton has to be the same, because all you can do is to replace a hydrogen in an alkane with the chlorine. You can't change the carbons around. So we can just redraw that same set of carbons like that, but without the chlorine on board. So you have that, and it needs to react with chlorine to give you that product. And remember, you always get HCl as the other product when you get one of those substitution reactions. So that's the equation, and the essential condition, remember, is UV. Okay, so you need UV light for that mechanism. The type of reaction is radical substitution, so that's a mechanism that you need to have learnt. So it doesn't ask for it here, but it would be a good time, if you're thinking I don't really remember that, to go back over it. Learning mechanisms means going through them time and time again until they're really stuck in your brain. So that's the mechanism for that, and that's what the UV is for, to generate the radicals. And then it wants to know why the percentage yield is low. Percentage yield means that, looking at this equation, it tells you that in principle, however many moles of this you start with, you should be able to get that many moles of product. But percentage yield says, yeah, but really in the real world you won't. With you, you'll get less than the number of moles you started with. And it's asking you why in particular in this reaction should that be the case. And that's something I often ask you in relation to radical substitution, because the point is that when the chlorine substitutes for a hydrogen, it won't necessarily substitute at that position. It could substitute here, or here, or here, or here. So there are a lot of potential products that could be formed, not just the one you want. Moreover, it could substitute more than once. There's no rule that says chlorine can only substitute once, so it wouldn't be surprising if you found that you needed more than one, that you found that you got more than one chlorine substituting in on occasion. So we can write that down and say that chlorine can substitute in at different positions in the molecule, and you might want to count how many, just to check how many products that would predict you'd get. And potentially more than once. So a mixture of products is formed. You have to say why there's a mixture. Don't just say mixture of products is formed. You've got to say why that's the case. Okay, so that's the answer to the question. If you wanted to count how many products, you could put chlorine at that position, would be 1. This one, which is the one you want, would be 2. You could also go there, which would be 3. And then there or there would give you the same product, because those 2 methyl groups are the same. So actually 4 possible products you could get. Next, it wants to know how you could make that starting from either of 2 possible alkenes. So with alkenes, remember, it's addition reactions, and if you want to put 1 chlorine in, you're going to add HCl, not Cl2, because that would put 2 chlorines in, but HCl adding across the double bond. And so you can see the reason there are 2 possibilities is that you could have the double bond either there or there in principle. So our 2 alkenes would be this one or this one. Always with alkenes you have to consider the possibility of EZ isomers. So you might think, aren't there even more than 2? But you can see in both those cases that there is no EZ isomer, because you've got 2 hydrogens at that end of this double bond, so that would mean if it flipped over it would still be the same. So there's only one version of that alkene, and the same with this, because you've got 2 methyl groups at one end. If you flip them over it would still be the same. So those are the 2 possible alkenes, and either way you would just react with HCl to produce that. And in both cases it's just an addition reaction, because you're just adding, in this case, H to there and Cl to there, or H to there and Cl to there. So you're just adding, you're not getting any other atoms removed, so there's no other product. It's an addition reaction. So the type of reaction, addition as we've said, but again it's a mechanism that you need to have learnt, which is electrophilic addition. So again, good idea to revise that if you can't remember what that means. And then it wants to know which of those would work best. And this, remember, is the Markovnikov thing. It's about understanding the intermediate that's formed during the mechanism and thinking about the fact that you can form alternative intermediates. So let's just do it for this one first of all. And you can see that when you add HCl, if you remember the mechanism, it adds like this. So you have delta plus, delta minus, and that's what happens. So the pair of electrons leaping out from the pi bond being grabbed by the hydrogen. Meanwhile that bond breaks and the electron pair goes out onto the chlorine. Now when that happens, this hydrogen could either go onto that carbon or onto that one. So you get alternative possible carbocation intermediates. If the hydrogen goes onto this end, you get a positive charge here. If the hydrogen goes onto that end, you get the positive charge there. So these are the possible carbocation intermediates. And remember, what you do is you look at where the positive charge is and you say how many other carbons is that carbon attached to. So for this one the answer is 2. So that one is a secondary carbocation. Whereas this one, the carbon with the positive charge, is only attached to 1, so that one is a primary carbocation. Now the reason for doing that comparison is that you learnt the order of stability. Tertiary ones are the most stable, we haven't got one of those. Secondary is next, primary is the least stable. So we say secondary carbocation is more stable than primary. And if it's more stable, it's more easily formed, because it means it's lower in energy, so it's more likely that the molecules, when they collide, will have enough energy to reach it. So more stable than primary, therefore more easily formed, and therefore it leads to the major product. So what does that mean? Well, the major product is formed, or either product is formed by this, that this Cl has broken off as Cl minus, remember, in both cases, and what it will do is just plug its electron pair in like that into the positively charged carbon. So you can write curly arrows like those, and you can see that wherever the positive charge is, that's where the chlorine ends up. So the major product will be this one, which is what you want, okay, which is the desired product, so that's good. Now if we do the same thing for this one, then I won't write out the mechanism in detail again this time because you know the story, but the possible carbocation intermediates would be this one, if the hydrogen adds to that end, or this one, if the hydrogen adds to that end, you get the positive charge here. So this time you have secondary or tertiary. And so this time the tertiary one is the more stable one because it's got the 3 carbons attached. So that one is more stable, which means more easily formed, which means leads to the major product. So what will that be? Well, again, that's easy because wherever the positive charge is, that's where the chlorine ends up, because it just does that. Okay, so it's going into that carbon there. And so the major product will be this, which you can draw like that if you like. And that's the wrong product. It's got the chlorine in the wrong place. Okay, so wrong product. So to answer the question directly about the better yield, the answer is this one will give the better yield, because the major product means you'll get more of it. So this one will give the better yield with 3-methylbutanene, which is what that compound is. This one will give a worse yield of the desired product, because the desired product should have had the chlorine there. Okay, so Markovnikov, it's very important to keep practicing, because that's a relatively complicated story, but it's always the same issue, so if you've got to grips with it, it's not too hard. Finally, in part E, it wants to know how you can make this same haloalkane starting from an alcohol. And that in some ways is the simplest of these reactions, because it's just a straight substitution. So an alcohol, remember, is a compound that has an OH group. So all you need is to draw the same thing, but just with an OH where the chlorine is. So that's the alcohol you need. Something you're going to need to get used to, so I may as well mention it now, is that when you draw these, you've got to make sure that the bond connects to the oxygen. Because really, the structure of that alcohol goes like this. So it's carbon, bond to oxygen, bond to hydrogen. So if you write it like this, they'll mark it wrong on the grounds that it looks like you think the hydrogen is in the middle, which obviously doesn't make sense. And if you kind of decide to hedge your bets and write it like that, so that it's kind of in the middle somewhere, they'll still mark it wrong. They want to see clearly that you know that it's the oxygen that's the one that's attached. So always draw those things very clearly like that. Okay, so that's the alcohol you need. The substitution reaction is done by reacting with sodium chloride and concentrated sulfuric acid. So that's the condition that you learn. So NaCl, concentrated sulfuric acid, and heat. So those are the conditions. You can write the equation in two ways. I think probably the best way, which sort of fits in most obviously with that, is to write the separate ion, because essentially what you get are Cl- ions from the sodium chloride and H+ ions from the sulfuric acid. So you could write the equation like this: plus H+ plus Cl-, chloride from there, H+ from there, and that gives you the product there. And you can see that the OH-, which is lost from there, combines with the H+ to give you water as your other product. If you just wrote HCl instead of H+ and Cl-, that would also be fine, because in effect you can think of it as that mixture generating HCl in the pot. If you want to know why you use that mixture rather than just adding HCl directly, it's that the mechanism of this reaction involves catalysis by H+. So the higher the concentration of H+, the faster the reaction goes, and you can get a higher concentration in conc sulfuric acid than you could just in hydrochloric acid on its own. But you don't need to know that. You don't need to know the mechanism of this reaction. You just need to know the conditions, be able to write the equation, and to explain that it's a substitution, which is the other question it asks. You don't have to say what sort of substitution for this one, because as I say, it's not a mechanism that you need to learn.